Okay, we're starting a volatile session to have a wonderful ending to this very exciting day. The first presentation on Lunar Volatiles Network, A Ring Around the Poles, will not be given by Bill Farrell, but it will be given by Rosemary Killen, who works very closely with him. Thank you.
Hi, I'm representing the Dream 2 team, and I'll be talking about lunar volatiles. Okay, so we've heard a lot about lunar volatiles, especially polar volatiles already today, but these are really just beginning to be understood. We know from LRO that there are deep hydrogen reservoirs, but what I want to talk about is, are these deep hydrogen reservoirs connected or disconnected from the surface frosts? That's one question. We have evidence of hydrocarbons, and that's another question. Where did these volatiles come from, and how deep are the reservoirs, and how patchy are they? That sort of thing. We don't really know. So we know from infrared that there are hydroxyls at mid-latitudes, and we know that there is OH at the equator. And what we want to investigate is, where are these hydroxyls produced? Where are they coming from? Where are they going? So this, to me, is the interesting question. It's just a schematic. We know that protons come in from the solar wind, and a lot of things happen. You have reflected protons. You have reflected hydrogen at slightly lower energy. And you have the production of OH and hydrocarbons. So you also have meteoritic infall. But what volatiles do they bring in? Do they actually bring in volatiles, or do they vaporize volatiles from the surface? And that's a good question. So this is a sample of the data that we've found in the last decade, basically. Epoxy, this is a clear OH signature at 2.8 microns. We have from Kaguya reflected protons. The reflected, the red outside of the reflected protons is actually solar wind. It's not, but you see the reflected protons in a slightly a lower energy band than the incoming, obviously. So you also have methane, which we've known about for a long time, and it obviously evaporates at dawn. But what we don't know is, what is the methane concentration during the day? What's the concentration at the surface at night? We don't really know that kind of detail. We do know there's a dynamic variation of OH with time of day and with latitude, especially with latitude, where you have the OH concentrations zooming up towards the polar regions. There seems to be a dawn-dusk asymmetry, but it's not really as dramatic as the variation with latitude. Okay, so this is an interesting graph, and what it shows is that the hydrogen deposits seen in the neutron are spread from the current polar region to the ancient polar region. I mean, the uncertainty here is that we don't have high spatial resolution. We don't, but it's an interesting question as to whether these deep hydrogen deposits are ancient and decoupled from the surface frost, or whether they're fed from the surface frost. You can see the frost is very concentrated in the permanently shadowed regions. It's connected with the surface temperature. And this really tells us that the surface frosts are in dynamic equilibrium with the incoming processes, the interplanetary medium. But if you look at impacts, this is a simulation from Dana Hurley. The volatiles really don't travel very far. So the evolution of a water plume, most of the ejected water stays local. And I think that's really important. But one of the questions is, if OH is produced by incoming solar wind protons, which we believe it is, then the OH migrates poleward. But does the reverse also happen? Does the OH migrate from the polar regions back to mid-latitudes? And this is it's really an unsolved question, as where do the volatiles come from? Where do they go? Do they migrate back and forth? Do they migrate from the surface frost to the deep reservoir? Is there a connection or a disconnect? This is a recent map of surficial OH. And it's a great map, but it doesn't tell us where the volatiles come from, which way they're migrating. And it doesn't tell us whether there's a connection between the surface frost and this deep hydrogen reservoir. Are these reservoirs connected, or are they disconnected? And if the hydrogen reservoir is an ancient reservoir, then why do you see the hydrogen extending all the way from the present pole to the ancient pole? To me, that's a good question. Is it truly a deep ancient reservoir, or is there some kind of a connection between the surface presently produced ice and the ancient reservoir? So so the questions we'd like to answer, and which we think we can answer with the lunar volatile network, is do the molecules and other volatiles actively migrate poleward? We think they do, but conversely, do the volatiles migrate back from the polar regions to the mid-latitudes? Is the modern frost locally generated? And if so, is it connected with the deep reservoir, or are these two reservoirs completely separate? Is 10 centimeters enough to separate the modern hydrogen cycle from the deep reservoir? Diffusion theory would suggest that 10 centimeters is enough to completely disconnect the reservoir from the surface. But that is a theoretical result, which I happen to have done. But and the other question is the space environment connected to the volatile production and transport? So how do we answer these questions? Well, we can answer it if we have a network of instruments in various places around the moon. Well, of course, 32 stations is a lot, but you could put as many stations as you can afford and try to figure out where what the cycles are, and try to draw out the migration of volatiles. So what would these volatile landers have? Well, you would want UV, infrared. You would want to measure the plasma and dust. You might want to drill at one or two areas. You might want a release experiment. Release some volatiles and measure where they go. And you can use orbiters, an orbiter with the landers to feed modern models of volatile transport. So okay, this is an aside. You could put one in a South Pole crater like Cabeus, which obviously would not be a long-lived lander, but would give you a lot of information on the hydrogen reservoir. So in conclusions, this is as a concept is just loosely defined, and obviously the drawback might be the cost. We might not have a flagship, but with the push to the moon, it's more and more likely that we're going to want some kind of a volatile network to figure out these questions of really where are the volatiles, where are they coming from, where are they going, and how long do they last. So that's my major slides, and I thank you for your interest.
So stick around. Okay, we're going to continue and have a panel as we did before after all of the speakers, so be keeping your questions in mind and we'll press on. The next talk will be Faustini and Slater craters, PSRs containing geologically young craters by Kathleen Mandt.
All right. So now we're getting close to happy hour, so I will not take too much of your time. But what I want to do is focus primarily on two unique locations that have a lot of science potential. And I'm focusing mainly on the science because it's lunar science for lunar landers at this meeting, and that's the main focus that I want to draw attention to these locations. Now, I haven't done a study on feasibility as far as landing here. This is probably longer term as far as our technological capabilities go, but the science potential for these sites is very high. So before I go into that, I want to emphasize that if we really want to understand the volatiles on the moon, we really need to go inside a PSR. A lot of the studies have been focusing on regions close to PSRs because of technical feasibility. We need power in order to do science with a landed mission, and solar power is the most reasonable way of getting power. We might be able to use lunar power within a PSR, but that is difficult to acquire. So one of the major areas for technical development is going to be power sources, particularly for PSRs. But we really, if we want to maximize our understanding of volatiles for human activity on the moon and for science, we need to go into the PSRs. Now, for science, I particularly want to emphasize the origin of volatiles in the inner solar system. That is something that we talk about the moon being a cornerstone for the history of the solar system with the impact history and the other history of the moon. But this is also true for volatiles because the volatiles that are trapped in the poles could be a record of the history of volatiles in the inner solar system, at least as long as they have been trapped, depending on the stability of the poles of the moon, of the orientation of the moon. So it's very important that we go into the PSRs and we study the volatiles and their composition so that we can understand their origins. So two sites that I want to bring attention to are areas that we have discovered with LAMP to be of interest, and that is the Faustini PSR and the Slater PSR. That's here and here. We just recently named Slater because it was an unnamed crater, so we named it after one of the scientists who helped to design the LAMP instrument. And these were discovered with LAMP. Now, LAMP is not like LROC. LROC is able to discover fresh craters by looking at older images and newer images that were taken under the similar lighting conditions and seeing a crater in the newer image that wasn't there before. We are not able to do that with LAMP because we are photon starved. We have to take several orbits and sum over those orbits in order to make these maps like we're showing here, which is the Lyman alpha albedo of the South Pole of the moon, and the darker regions are the permanently shaded regions. We interpret the darker regions of the permanently shaded regions to be because the top microns of the regolith have a higher porosity than the surrounding, or than sunlit regions. We don't really know why this is. This is another reason to go to a PSR, study the environment, why it would have this effect on the regolith. But we did notice that when looking at these two PSRs, that there were two patches in regions that do not experience sunlight that have brighter albedo in the Lyman alpha compared to the surrounding PSR region. Now, these brighter regions coincide with the ejecta blankets of two craters that are about 1 kilometer in diameter. And we've interpreted that to mean that the formation of the crater wiped out the highly porous regolith on top of that area and created an area that's bright in Lyman alpha. Now, we looked at the mini RF observations, the CPR of these two craters as well, and the ejecta blankets of both of these craters are also bright in CPR. Now, the CPR could indicate water ice, or it could be bright because of surface roughness, and in this case, it's most likely bright because of the surface roughness of two geologically young craters. So here, we have two locations within PSRs which are already interesting because they're permanently shaded regions. They probably have volatiles, but we also have two geologically young craters that we could explore in one location. So we've estimated on very limited data an upper limit for the age of these craters based on what we can understand right now about the transport of dust on the moon. This is extremely limited data, something we need to measure with a lander. So if you put a lander, measure dust transport. But we set an upper limit of about 420 million years. With the mini RF, we're able to constrain the ages a little bit better because of the degradation of a discontinuous halo, and so we have an upper limit on this crater of 75 million years, and then this crater is about 16 million years, so it's younger of the two. So each of these locations is interesting. They're in a PSR, there's going to be volatiles likely in the PSR, so that's going to be valuable. And then we have two young craters. Now, Slater is interesting because it's the youngest of the two fresh craters. There's also a larger area that has view of the Earth in this Slater crater, but it's not quite as cold as Faustini. And in particular, Faustini is interesting because of these two, because of this crater here, which is one of the coldest areas, and it was in a previous presentation pointed out as one of the areas where most of the SKGs could be, or most of the questions could be addressed from the SRIM report. So Faustini is particularly interesting because of that. It's important, mobility is going to be necessary if we go to these craters and explore, so that's going to be something that's important. And then the science objectives can be divided into 3 categories. And these science objectives are all relevant to SKGs and to the SRIM report. So for lunar volatiles, what we would want to know is how water ice varies spatially and with depth, because that's an important thing that we still don't understand, even with all of the data that we're getting from LRO. We don't understand with depth and we don't understand spatially, so this is something that we would want to explore. We would want to know what the bulk composition of the volatiles are, because water isn't the only volatile that's there. It's not the only volatile of interest for ISRU, but it's also very important to understand the composition of other volatiles for the origin of volatiles in the inner solar system. The L-cross plume example is prime example of why this is important, because a lot of the volatiles that showed up are things that you see in a comet. So are comets the primary source of volatiles in the permanently shaded regions, or do we have other sources? Is it a mixture? And measuring the composition, particularly the isotopic composition, would be important for understanding the history of volatiles in the inner solar system. So before we go and use these volatiles, let's go study them and see what they are so that scientists can connect it to the bigger picture of the solar system. We would also want to look at regolith processes in the permanently shaded regions. This is a foreign environment that we don't know very much about. So if we're in the PSR, we would want to know what is happening to the regolith. Like for the example of the LAMP observations, why is the upper layer of regolith highly porous compared to the other areas of the moon? And we don't fully understand that, but there's something that is happening in the permanently shaded regions. You could literally map what is shaded and what is sunlit with the LAMP observations in Lyman alpha. Why is that? And then there are different processes that have been suggested to only take place in the permanently shaded regions. One is dielectric breakdown. From the crater team, they've been studying this. And is this process happening in the permanently shaded regions, or is it not? It would make the regolith, the grain size of the regolith smaller, and it would also influence the space weathering. So there's a lot to study about regolith processes. And then, of course, if we visit a geologically young crater, then we could start studying impact processes in this unique environment of a permanently shaded region. So I'm not going to go into the detailed experiments for the sake of time, but there are short-term experiments that could be done on just a less than 1 day time period, and then long-term monitoring with roving as well. We would want to monitor the exosphere, the dust environment, measure the volatiles at depth and space, and look at the volatiles with distance from those fresh craters and see what the cratering process does to volatiles that are in the permanently shaded regions. Do they wipe it out? Do they redistribute them? So that's another thing to look at. The unique environment of the PSR does require technology development, particularly when it comes to power systems. One thing that we're doing at APL, working with Penn State, is developing a power source that could last for about 10 Earth days. So this could be useful in a permanently shaded region. We're currently developing it for Venus, and it's also applicable to Europa, but it's a combustion-based power system that doesn't have any emissions, so it wouldn't interfere with the measurements that are being made. And so if you're interested in learning more about this, I can put you in contact with the PI on this project. So in summary, a landed mission inside of a PSR is necessary to really understand the volatiles on the moon. We need to go to the PSRs, so we need the technology development that's going to get us there. Faustini and Slater PSRs are unique because they have fresh craters. And it's good that I'm on the right slide. But they have fresh craters that would allow us to study impact cratering processes and volatiles within a PSR. So it's a really interesting environment. But we need mobility to do that, and we need technology development. So that's it.
Oh, I know the next speaker. All right, moving along. We're going to continue with landing at ice exposures on the lunar polar regions by no one else other than Shuai.
Thank you, Carle. Hello, everyone. Today, I'm going to share some work we've done recently about landing at ice exposures in the lunar polar regions. As we know, the water can be accumulated at the PSRs in airless bodies because only a few millimeter water can be sublimated in billions of years at a temperature less than 110 K. And we find this case on Mercury and Ceres. So this is the I didn't try anything. I just want to use the pointer. Yeah, here this plot, this is Earth-based irreversible radar data. Look at the Mercury North Pole, you can see very high radar reflectivity. And this is a messenger, the WAC camera. We can see in this purple rectangle region, we can see enhancement of the reflectivity in the visible image. And also similar case on Ceres North Pole, we can see in the permanent shadow regions, the very enhancement in the reflectance. However, we don't find such case on the moon. Until recently, we looked at the M-cube data in the permanent shadow regions, look at the scattered light very faint, and we find it as absorption features as shown in this plot. These are average spectra of thousands m³ pixels. This is the North Pole and the South Pole. We can see very distinct absorption features centered around 1.3, 1.5, and 2 micron. For reference, the blue line in the red plot shows the pure ice spectra measured in the lab. There are two possible scenarios for this kind of ice on the surface. It could be mixed with the regolith intermittently, or it could be patch ice mixed with the dry regolith. So we did modeling, and we get abundance for roughly, if it's mixed with the regolith, it'll be around like a 30%. If it's like a patch ice linear mix with the dry regolith, it will be around 20%. Anyhow, it is way lower than what we see on Mercury and Ceres, because on Mercury and Ceres, it's relatively pure than on the Moon. So this is the distribution of the ice exposures we see on the North Pole and the South Pole, as shown in those green and cyan dots. In this region, it also shows low temperature, mostly less than 110 K, as shown in the middle plot, and also show high lunar albedo. We can see it's above the average, and also one standard deviation higher than the average value of the North and the South Pole. However, the distribution of these ice exposures are very patchy. In the most red plot, showing all the pixels, shaded pixels we examined, and we can see only a few % of them has water as exposures. What I mean, water as is molecular water, not a hydroxyl. So, looking at these exposures has several significances. First, water ice can be very important in situ resources for utilization, as we discussed a lot today. And also, it's critical for us to understand the unique process of the deposition, transportation, and retention of ice on the Moon, because it's different with Mercury and Ceres. So we need to understand why the distribution of it. I think I just skipped. Oh, sorry. Yeah, so we need to understand the distribution of the ice. We plotted the exposure with the temperature. And in this plot, I just showed the diviner annual maximum temperature below less than 110 K. If it's above, it will be white. So we can see all the exposures are associated with those low temperatures. However, not all low temperatures show ice, such as on the North Pole, we see the Bosch crater, and also in the corner, a lot of macro cold traps, we don't see ice exposures. And on the South Pole, a lot of cases, craters are very obvious. For example, the Amundsen crater, and also very, and the rest too. I wanted to emphasize here that we're just examining the surface, superficial ice. So I know there is a talk at the end of this session talking about Amundsen crater. So don't worry, that could be water beneath the surface. But we don't see on the surface. And this distribution pattern is very interesting because we look at the true polar wonder map proposed by Matt Ziegler et al. This is I want to use the project. Yeah, it works. So this is the ice stability depth when the Moon was on its paleo axis. And it's interesting, if you look at the outliers where you see low temperature now, but you don't see ice exposure, the ice stability depth is way thicker when the Moon was on its paleo axis. And we did a simulation at the Faustini crater. So this is on its chrono axis. This is on paleo axis. I didn't synchronize them. If you synchronize them, you will find that there will be way more light scattered into this crater when the Moon was on its paleo axis. And it should be the same case on Amundsen and these craters when the moon was on its paleo axis. Now, we still need to understand why the ice abundance is low and also is so patchy. And we think this is maybe related to the slow supply of water ice and also the fast overturn of the top layer by impact. Recent studies and also a lot of previous studies show that the top 1 meter ice sitting on the surface, it can be wiped out by around 500 million years on the moon. However, on Mercury, it can be 3 billion years. So the overturn, the impact process on the moon is way faster. And if you don't have enough supply of water ice, all the ice signatures can be wiped out by the impact. So that could be more ice beneath the surface or in the deeper because that region has not been affected by the impact. And we proposed several possible landing sites for us to examine these ice exposures. And we found that most ice exposures on the North Pole are mostly associated with the crater walls. So the topography is very rough. It could be very hard to land on them. So we picked up several locations on the South Pole. This is the Sverdlov crater. Again, the red dots are the possible ice exposures, and the base map is WAC. And you can see this map. This is a long exposed neck image. And if we zoom in, this is the top DM data, 30 meters per pixel resolution. And we can see in this region, around a few kilometers, the mean and maximum elevation is around 250 meters. And we can it's very smooth, so it's possible for landing. Similarly, we found another location. It's downside of the Sverdlov crater. And this is just 2 examples. So you can zoom in a lot of other regions at this crater. You can find a smooth region to land. This is for the Hayworth, Shoemaker, and Faustini crater. Again, we can zoom in and find a relatively smooth region to land and also has some ice exposures. I want to point to the Faustini. It's very interesting. You can see most of the ice exposures is located at the direction along with the paleo axis. So in summary, landing at these ice exposures may help us to constrain the thickness and also the abundance of these deposits. And this is important for future utilization of these resources. We need to drill them because it could be a thick layer, not only at the top surface. We can determine the thickness. And also dating the age of these deposits may help us to test the true polar wonder hypothesis. These ice might be very old because after the moon moved to its current axis, we don't see ice deposits at Amundsen crater. So it could be very old deposits, and also the supply of those water is very slow. And also, if we measure the rate of hydroxyl or molecular water migration, this may also help test our hypothesis. So we predict the migration of those molecular water should be very slow. And also, we can test these hypotheses about the gardening effects. It could be more water beneath the surface. So if we can drill them, then we can determine whether some ice beneath the surface. So that's it. Thank you.
Oh dear, the next speaker. Science enables exploration, and exploration enables science. Exploring the lunar pole volatile deposits by Clive Neal.
This will be an adventure. Where's Mark Robinson? He's not here to see his logo that he sent me. But crediting the LROC team with this science enables exploration and exploration enables science, saying that Mike Wargo also championed, but This is something that is sort of condensed into exploring polar volatile deposits. So let's see how we go. I mean, if we look at the data that we have, we're using these neutron data. They have a very large footprint, and it seems as if they're in and around some of these permanently shaded craters or shaded regions, and they're called neutron suppression regions in some of the LEND papers that have come out. So the important thing here is that we also know that volatiles are notoriously difficult to sample and preserve. So in situ science becomes very important to explore these regions, not only for understanding the origin and evolution, formation thereof, but also tied to the hip with the exploration potential. So it's important to think about the exploration of these different areas in terms of science and exploration. And this gives us an example of a low-cost, high-return mission, example of LCROSS, to give us ground truth into some of these exactly, or at least an idea of what is there. And it's much more, as Kathleen said, than water. There are other things as well that are important scientifically and also in an exploration sense. So thank you, LCROSS. So if we look at the science, or focusing on the science, we know that the capable missions to these areas can give an abundant dividend in terms of the data that they're going to return to us. And the last decadal survey actually did look at this lunar polar volatiles explorer concept as a mission, and noted that this was a high priority subject that was, or a topic, science topic, that should be examined in the next decadal survey through future missions. Now, to sort of turn that around, between now and 2025, there are at least 6 landed missions proposed to the lunar South Pole. One of those, as we talked about a bit earlier, is Resource Prospector. That's the only one from the US. The rest are international. But there is international interest in exploring these regions, and I think it's important to leverage that from where we can go. So partnerships between science and exploration become very opportunistic in terms of getting that dividend of data that benefits both communities. It's the same data as LRO is proving time and time again that can be used to give those returns. So the League Volatile Sat report, the second one that we did, actually started to focus in and used a similar approach as David talked about, with slightly different parameters. So you will see some differences between what David presented and what came out of the League Sat report. But both the South Pole and the North Pole offer very intriguing mission scenarios in terms of actually trying to develop those types of missions. And you can see down, God, this is really weird. And you can see down here, this gives us an overlay of the South Pole and the North Pole, and I'll go into the parameters a little bit of how they came up with those overlays, but the blue represents the areas of interest. And you can see in the South Polar region, Amundsen, based upon the criteria that we used, did not stand out. But you can play with them, and if you go down, as James said, to 125 ppm, you actually start to see a lot more areas that are interesting. So some of the places that, if we want to go here, it's difficult. There are extremely cold temperatures, and there are very significant slopes if you're trying to traverse into them. And then if you land directly, you have to deal with, well, how is my landing going to disturb what I see at the surface, and how am I actually going to survive long enough to actually do something significant? So we require capable missions. All right, there we go. So in terms of science, then, we want to understand the origin of such volatiles, the endogenous versus exogenous origin, understand the lunar volatile cycle that we've already heard about. We want to investigate the delivery, if possible, to the inner solar system. But as Shuai is saying, this may be very slow, especially in terms of mission lifetimes or human lifetimes. But an astrobiological bent on this is, do these volatile deposits contain the building blocks for life that were actually delivered to this planet and hence are responsible for this, what we have now? In terms of exploration, we want to define the distribution of such deposits within the various PSRs and understand the form that these volatiles are in. We want to explore the regolith geotechnical properties because we want to extract these. We want to get them out, and can we actually do that given the extremely low temperatures? And then quantifying the processes, or quantifying how to process these materials, transport, store, and then use potential life support and rocket fuel consumables is also part and parcel of the data that are going to be needed in order to use these particular deposits. So just as a sort of a notional concept, you've got the arrow going down. That's the increasing complexity of mission types. And we can argue about the semantics, but this is my talk, and that's what I came up with. So we've got the low-cost L-cross type missions, an impactor in and look at the plume that comes out. Maybe penetrators that can go into a large PSR and look at the distribution at a very short-lived, contain spectrometers to be able to look at what's at depth there. Static landers direct to a PSR. They could be RTG-powered rovers associated with that, or RTG to power those landers so they last a bit longer. We talked about the resource prospector type mission, short durations visit to accessible PSRs, then more capable RTG rovers that would land in sunlight and traverse into PSRs or land directly if possible. And then hoppers, and I was excited to see some of the commercial presentations this morning looking at that vertical launch, vertical land, and back again, this reusable concept of hopping between or within a given PSR and then maybe between different PSRs. And I find that to be very exciting in terms of development. So the VSAT-2 report actually came up with initial data, what we would want to see, and I've laid it out here in a very broad approach, not saying what you would need, but we did have, types of instruments that would be useful, not to be prescriptive because everybody will come up with something better, and that's the good thing. We can come up with other things that would allow us to then be able to get the data that are needed to answer these science and exploration questions. So strategy then for exploring initially in situ science. We need to understand what we're looking at before we try and bring it back, because then we don't understand how it can be degraded, and we may be getting a false positive, so to speak. So mission 1 and 2, or mission types 1 and 2, could be deployed to large neutron suppression areas deep within PSRs to actually get ground truth from more than just that little bit in Cabeus. Mission types 3 and 4 could be deployed in craters that are in partial shadow, and Amundsen is part of that as well, and that should be included here. But there are those that do afford these types of initial in situ analysis that would support sort of dipping a toe into the cold trap and coming out again to warm up before going back in for more. And then we start to get more complicated and expensive missions where we're trying to go between different PSRs and actually map out, maybe within one, what is the grade of that ore body that we're looking at. So technology development is going to be required to do this. Again, we've got rovers, we can build a rover, but remember what it's got to survive in. And that is something that does require some thought. And again, if we end up doing in situ and then going to sample return, we've got this cryogenic, and we can define cryogenic whichever way we want, but to preserve the stratigraphy, to preserve the integrity of the sample that you're actually getting is going to require some technology development, and that starts sampling, transport back, curation. Preserving it for future generations becomes then a major challenge. And I put in here also the tech demos on the surface, in situ resource utilization, actually in situ. Going to the moon and actually producing that. Now resource prospector would be our first stab at that, and that's why I got a little passionate early on. I'm getting frustrated. Can we just go do it already? I mean, it's so it's this is something else in terms of the technology development, that if we are going to have these resources to be enabling, we need to show that they can be enabling. So I end up with a landing site recommendation. This is down here on the, if we look over here on the left side, these are the criteria that we used in the overlays to create these maps for the North and South Pole. And I'm focusing on the North Pole because Peary, the Peary vicinity represents or meets the general criteria and potentially has Earth visibility. So there's also substantial areas on the far side, but I focus in on Peary because it is in partial shadow. You don't have to deal with the slopes as such as if you're going to traverse down that crater wall. You can land in that crater and you can go in, you can come out and warm up. So you could use maybe a resource prospector type rover to actually start doing some really good in situ science in a PSR that we know has significant water equivalent hydrogen. And so, exploration and science synergies are basically really exemplified by going to actually explore these polar volatile deposits. And we've heard earlier today that there is private industry interest in actually doing this and exploiting the potential for exploration. There's also international interest in these particular deposits. And again, I point back to the 6 landed missions that are proposed between now and 2025. So it's, and only 5 of those are non-US. So it becomes highly relevant to the international partners. And then initial in situ investigations will lead to cryogenic sample return that we can then come back to terrestrial labs and do much more with them. But we need the technology development. But the important selling point here, this is a test bed. This is a feed forward to other cryogenic sampling, comet sample return. Also Mars. There's apparently a little bit of water on Mars too. They keep finding it. And then ocean worlds. So these are potential feed forward sites, and we've got our test bed pretty much in our back garden. So thank you very much.
Do we have the next speaker here? We don't have his presentation, so I think if we could have all the presentation people come up and we will have a panel discussion then. So be thinking of the question that these 4 speakers have stimulated. And as soon as they get up here and get settled, we will open the floor for questions. Okay, we'll start over here, and then we'll go to you, Jack. Mm-hmm.
So, Clive, I guess this is a question for you. I was intrigued by your question. You're the first person I've seen talk about penetrators. So I was going to put in a plug for penetrators. Seems like a great technology. Ames used to do a lot of that in the olden days, and I'm sure we could dust some of that stuff off and make use of it. The other one I wanted to talk about, though, was you mentioned the idea that technology development was going to be required. And I was just kind of wondering what your thoughts were. I mean, we're having a hard time now, you know, getting anybody to focus on the moon, at least historically. Hopefully that will change. But I was wondering, is anybody talking to like STMD about, you know, the technologies that would specifically be needed to go carry out these kinds of investigations? And is there any possibility between collaboration between STMD, SMD, and the commercial community to go make this happen?
Well, that last one sounds like a question for Jim, and Victoria is having a seizure over there, so I think, can you go use the microphone, Victoria?
Oh, we've got a box here we can give you.
Oh, we got a box we can throw. All right.
So, Andy Petro, raise your hand. STMD is here, Space Technology Mission Directorate is here. HEO and SMD, we are all collaborating in exactly that way and looking at technologies, advanced exploration system, not only is developing technologies, near-term technologies for human exploration, for example, on the space station, but we're also looking at investments in longer-term technologies. We're partnering with Space Tech also on the same thing, for example, with Science Mission Directorate on MOXIE, the ISRU demonstrator on Mars 2020. And that's just, I mean, that's not even the tip of the iceberg of the investments that are collaboratively going on between the three directorates. So Andy, you should say something at some point while you're here.
Throw the box at him.
Throw the box at
Throw
him.
the box at him. Yeah. Have the box. Catch.
Okay, just talk. Yeah.
It's meant to be.
Is it on?
I'm from STMD, that's why I'm here. Been making notes. Sort of switched on. Is it?
Anybody got a hammer? How do you switch it on?
Yeah, I was just saying that I'm here for that purpose. I've been making notes on everything people have been saying, but please do, you know, bring up these ideas where we need to be focused on developing technology. We do partner, as Victoria was saying. Of course, budgets are incredibly constrained, but we do the best we can. And I think the information we're able to gather here will help us prioritize what we really need to focus on.
Jack.
I have a quasi-theoretical question. In, I think, 63 or 64, Ken Watson and Harrison Brown did a theoretical study of volatile migration on the moon, concluding that, yes, volatiles will migrate to the poles. I don't recall that analysis, although I haven't read it in 5 or 6 decades, said anything about it migrating back, and I'm just curious of whether there is theoretical support. Jim Arnold came to the same conclusion a few years later.
Well, yeah, there was a recent paper by Farrell et al. It's called the Polar Fountain, where volatiles, I mean, you've got impacts at the poles just like everywhere else. So, and you have sputtering, and any process that occurs at the equator also occurs at the pole. So volatiles will be ejected from the polar regions, and they'll probably land at mid-latitudes.
Well, I understand that, but I think they kept that analysis. I think they had that analysis that the net migration was poleward. That yes, things are going to move back and forth, but the net is poleward.
Well, that's true, but yeah, I'm just saying that the reverse also happens, probably at a lower rate.
Now, another question related sort of to that is, do we know the age of the various craters in which we're seeing evidence of or no evidence of volatiles? Do we have some relative ages? Are the ones with volatiles older than the ones that don't have them? Do we know that?
As far as I know, it's related to temperature.
Well, but what I'm thinking of is you had during episodic periods a significant amount of volatiles, including water almost certainly, ejected into the lunar atmosphere by pyroclastic eruptions. But they all probably ended at some time, and I'm just wondering whether what we're seeing is old ice, or old water, rather than anything that's going on today.
Well, the question is, I mean, whether this deep hydrogen deposit is an ancient reservoir, and then the surface frost is a modern reservoir in dynamic equilibrium with the surface processes. So there are two reservoirs, one an ancient reservoir and one a surface reservoir that's actually in dynamic equilibrium with processes that are occurring today.
Yeah, but it may be related dynamically to the ancient reservoir, so to speak. And where you have a water deposit, I'm just wondering if that isn't all old water, even though it may cycle up and down.
But you're assuming that it all comes from the moon. It may not.
Well, I don't know.
And again, this is the thing.
Again,
we got to go. We got to go do some.
But it's only been recently that we've had indigenous water into the mix.
Yeah.
And the other question is how much of the delivery is from meteors. I mean, meteors, if the impact velocity is high enough, it's going to be a loss process rather than a source process. So
well, all the evidence is.
The ambiguity is how much comes in from various processes and how fast does it migrate to the poles.
Well, I think the evidence is that most of the meteor is lost, including the volatiles, particularly the volatiles.
Somewhere.
Well, no, I did a calculation recently, and the temperature of the impacts is not high enough to result in a great deal of loss, except for hydrogen and helium, and a lot of the other volatiles will be retained.
But we don't see much other in less volatile elements. We don't see much evidence, just a little bit, of meteor contribution to the moon. That's what I'm getting at.
Yeah,
Go ahead.
I totally agree with you. So it's highly possible the pericardic deposit water can go into the poles. However, we don't have any like a definitive evidence to detect molecular water. So recently, when we see those water exposure, molecular water exposure, they are very patchy. So I just give my data to someone else. They are trying to date the age of these deposits, whether they can find like some correlation, like whether they are old or young. Yeah, someone is doing the work.
Hi, I'm Pete Humphreys, AS, MS, Inc., and my colleague Miss Ashwari is here. So I'd like to bring up about the technology. Main key features I see is it must be flexible, these habitation modules. We have a VR presentation tomorrow, and the habitation must have a flexible approach for upgradability and reconfigurability. So if you've got a platform, what you put on that platform is the science community's what they want to put on it. And we all know the weight is the enemy. So if you want to come see me, Miss Ashwari will be doing a presentation later on. Thank you.
Carle.
Hi. I want to follow up on Jack's comment and the possibility that water migration nowadays may actually be from, just had a thought while I was talking, from the poles to the equator, because the water is paleo up there at the poles, old cometary water. Then current day micrometeorites and meteors will liberate the water from there, and we may actually have water originally in the poles and migrating down, and then perhaps going back and forth a little bit. Just something to think about. And other sources of water, the solar wind water is OH. Let's keep in mind that it's not going to be OH that's going to migrate around. When H2O migrates and sticks on the surface, it will probably can be absorbed dissociatively, right, and form OH in there. And OH is very, very stable at lunar temperatures, unlike at Mercury, where it would actually recombine at those temperatures above about 550 Kelvin. You actually have recombinative desorption to form H2O. The moon doesn't get hot enough for that, right? So OH is going to stick around as OH. The implanted solar wind, though, can potentially migrate around the H can and then degas, not probably as H2O, because you don't see evidence for, as I understand it, a reduced Rhine. I mean, we do see nanophase iron, but not a reduced Rhine. Instead, it probably migrates around as H2. What I find intriguing is that perhaps micrometeoroid bombardments themselves liberate water. And this isn't a new idea, that the grains are basically incipiently reduced with hydrogen stuck in there. When micrometeoroids hit them, then they have instantaneous increase in temperature up to a high enough level to cause this recombinative formation of H2O with the olivine and whatnot and forming nanophase iron, form water that way, which migrates around. But I think it's intriguing that maybe we have water migrating from the poles nowadays due to micrometeor bombardment liberating it, and that could be some of the water that we see going back and forth. Who knows? Any comments on that, right? Okay, comments on those thoughts, right? I mean, I was just kind of ad-libbing.
I don't see any disagreement.
I got a comment.
Oh dear, okay.
How would you test it? That's a question, actually.
You know, I think Dana had a good idea, or maybe it was already done by the Chinese when they landed. You drop a source there, see how it migrates. I think that'd be a very elegant test.
Yeah, yeah. Okay, Dan Moriarty.
Hey, this question is for Shuai. So in the North Pole, you pointed out that some of the water absorptions you were seeing in the M-cube data were kind of localized in the steeply sloped walls of the crater. So do you think there's like a physical process that's causing the water to accumulate there? Or is it maybe similar to something we see with like mafic materials where even if the abundance is kind of the same across a crater, on the kind of steeply sloped walls, you're inhibiting like soil development, which might mask out the absorption bands. So might the water abundance be kind of the same throughout the crater and just masked by soil development, for instance, on the floors or something like that?
So your question is, first is why it's always associated with the wall, and then the second is like you're trying to understand. Can you repeat the last question?
Sure. So is it just that you're seeing the absorption bands kind of well preserved on the steeply sloped surface of the wall, which inhibits like soil development, which might mask the absorption bands? Or is there a physical process that's causing like more water to accumulate specifically in the walls?
I think I don't think it's like any like a soil mask those features because on the South Pole we see all of them. I think it's because on the North Pole, all the PSRs, the region, the area is kind of a smaller. So they have PSRs, but the PSR, the region, you can see it's always associated with the walls. And it's not like the South Pole. The South Pole, a lot of craters are whole in the PSR. So I think that's the region, that's the reason. And it's like on the wall, it's the deep wall is cold enough to preserve those ice. Or it could be the ice originally it's on the floor or somewhere else, it's migrated to the wall because it's colder.
Very cool. Thank you.
Yeah. James.
Hi, so I had a quick comment and a question. So the first was I learned from some of my Russian colleagues, which I didn't know before, was that at least one of the Soviet lunar sample return missions landed, sampled, and left all during the lunar night. And it had to do this because actually it ran entirely on primary batteries and it would have overheated if it had tried to operate during the day. So when we were doing our lunar polar sample return studies, we sort of kept this in mind, and one thing that occurred to us is actually a lunar sample return mission from a PSR might actually be rather simpler to do than an in situ mission for getting comprehensive data about the interior of these craters, because you can go in, take your sample and get out without having to spend the time doing the detailed in situ measurements, and actually that can be something that maybe is worth considering as an addition to what Clive was saying. So I'd like to ask Clive his own question, which was, you talked about cryogenic sample returns. So for you, what is cryogenic and why?
Well, it's going to be cold. Yeah. No, I mean, there's, cryogenic minus 80, but 110 Kelvin will preserve much more than minus 80 in terms of integrity of the sample. That then becomes a trade-off between your cost versus your science return. At least that's what I've dabbled in this. That's what I've gleaned from listening to engineers in terms of well, minus 80 seems to be, yes, we can do that. You want to go to 110 Kelvin or less. It's going to cost you in dollars, and it's going to cost you in mass. So it depends upon what the goals of the mission, of the sample return mission are, as to how much money and mass you would put into the cryogenic aspect. But I think minus 80 is the standard that people would point to in terms of we have minus 80 freezers. But if you want to go more than that,
What do the comet people want?
Clive, it's not just bringing it back at minus 80.
Yeah.
It's storing it at minus 80, and then it's working on it at minus 80.
Yeah.
And so, great, you store it at minus 80. How are you going to get that into your machine to do whatever analysis you want to do without it thawing out?
There you go.
And never mind 110
so-
Kelvin.
so
I
there's-
mean,
there's-
storing things is pretty easy and straightforward,
Yeah.
but working on them, we're not going to have people in coats in a minus 80
Right.
lab, and then and that becomes more expensive. And you know.
Exactly.
I
So
think
this-
you can solve that once we get the samples, though.
We better solve it before we get the samples.
Yeah,
or-
samples won't be around for very long otherwise. I was going to say that, but I didn't.
Jinishi. Yeah.
Two questions. First is, I calculated the velocity, the thermal velocity of on the molecule, water molecule. In the case, water molecule, if we that they have 100 Celsius or 400 Kelvin, but the molecule could not escape from the moon because the escape velocity of the moon is very large. So before the Selene launch, I thought there are a lot of the water molecule produced by the solar wind or meteorite delivery. So that each molecule could not escape from the moon. Then all the such a molecules piled up on the surface of the permanent shadow area. So that I had thought the very thick ice layer produced in the permanent shadow area, but there is no such a case in a Shackleton crater. So I thought there are some another mechanism to produce to destroy the molecule or the escape the molecule. One there are some theoretical model, for example, like polar wonders, or the molecule was destroyed by the ultraviolet. Then the molecule becomes ions. Ions are picked up by the planetary magnetic field. Then they escape easy. So the low abundance on the surface of the polar region is, in a sense, reasonable. How do you think, Shuai, do you think any other explanation for the low abundance of the water molecule? Or do you think under the surface there are a lot of the water molecule? How do you think about it?
I think it's a good thought, but as Carle said, a lot of studies show that it's not easy to form molecular water on the surface by solar wind because the temperature is not high enough. That's one thing. The other thing, if the molecular water is in the vacuum, it's easy to be dissociated by the dissociation. So by the sun, it's not the molecular water is not easy to survive on the airless body. For your second point, I think it is possible we have more molecular water beneath the surface. A lot of theoretical modeling suggests that. But before we go there, we cannot say more. MCube data only see very top surface. This is one thing. The other thing, we just look at the scattered light. So the light is very faint, and also the signal-to-noise ratio is very low.
Yeah.
So a lot of uncertainty there. But from the few thousand pixels, I didn't do any further process. The average spectra definitely looks like ice. So we are very confident about the presence of ice on the surface, but it's harder to say how much now.
Additional comment. Actually, I calculated the thermal velocity for the 100 Kelvin or 40 Kelvin. Even such a low temperature, the distance for the molecule escape, molecule movement is for the 100 Kelvin, the case about 100 kilometer like that, more than a large crater. And but 40 Kelvin, the 45 angle escape, flying is just 50 kilometer. So that it's very interesting because Shoemaker and Cabot's the largeness of the cold area is 50 kilometer like that. So that once even 100 Kelvin places, the water molecule easily go out from that area. But of course, there are some molecules coming in, but 100 Kelvin. But even such a cold case, the molecule could be escaped if we ignore the absorption energy anyway. But 40 kilometer or 50 kilometer size, the water molecule once coming, and the next time that one cannot escape from the crater. So maybe the hydrogen concentration on the Shoemaker and the Cabez is a little bit larger. Maybe I think such a phenomenon occurred. Anyway, that's a comment. And another comment is for the Mercury's case. Mercury is very large, and the rotation period very low. So the night side is very large and long. So the such a water molecule, if that were divided in night side, then the water molecule could not easily destroyed by the ultraviolet because the night side is long time. So the Mercury's case is perhaps such a case occurred anyway. Okay, sorry, just a comment. And the next question, one question.
Hold on a minute, Junichi.
Yeah,
I think you and Shuai need to sort of talk at the poster session, to be honest with you.
Okay.
Yeah, volatiles are waiting.
Yeah, liquids are waiting as well. So,
short comment. Actually, sorry, I want to. Yeah, now we
and
are
you're still going.
Thank you very much. We are now very interested in exploring the water molecule on the polar region. But one reason for the scientists is that if we find the water molecule on the polar region, then we can say something for the delivery system of the comet of the something. But how do you think so? Why do you think so? Because if the molecule migrated from the other place, then the mass differentiation occurred. So how do you say that if we found deuterium or something, and how much are divided or delivered from the outside? So that we should answer such a case if we go to the polar region and if we want to say something from the exploration, water exploration, then how do you think?
Yeah, I think a sample return is very important. So if we can get samples from the polar region, like with those ice, I think isotopes can tell you their origin.
Yeah, so actually, I think someone
can we continue this later a little?
I have a question.
Okay.
Can I ask a question for Mr. Lee?
Okay, sure. One last question. Then I have a comment.
Okay, I didn't understand your comment that the overturn rate at Mercury is very, very slow compared with the Moon because the impact flux is much higher at Mercury.
That's based on the current impact flux on Mercury and the Moon. I didn't do the impact modeling work, but it's the one in my group. They did the modeling work. They suggest to erase 1 meter thickness top layer on the Moon takes 500 million years, but on Mercury it takes 3 billion years. I think Dana also has similar work to show this.
Is that published?
Not yet. It's under review.
Okay, before we head out to okay,
I was just going to suggest we go have a beer.
Yes, yeah. But except one moment though. There's one issue that I'd like to at least seed, and you can talk about over beer. And this has to do with science and exploration working together on some of the aspects that have been raised during this session. The accumulation of the water in the poles. Everyone is beginning to recognize it's very spotty. It probably occurs over billions of years. And as we've seen, there's resources and deposits at both the North and the South Pole. The exploration part would like to harvest this as best we can and most efficiently. However, as some of the modeling that Dana Hurley has done has shown how once you have an impact, materials distribute widely. And if we go to both of the poles with experiments, we're going to bring contamination. So something I would suggest discussing perhaps over beer is, should we limit our exploration to one pole and keep the other pole pristine for this sequence of solar system volatiles that we're eventually going to want to look at scientifically? So think about that, and let's go have some volatile sustenance.